Hello everyone, my name is Aniket Koul and today we'll be discussing the first problem from the CP-31 sheet by TLE Eliminators under the 1200 rated problems. I'll be moving to the CP-31 sheet and we can see that the 200 rated problems parameter has been checked and we can see a clickable link to our problem, that is 3 activities. So let's begin. The problem states that winter holidays are coming up. They are going to last for n days. During the holidays, Monocarp wants to try out all the activities exactly once with his friends. He can either go skiing, watch a movie in a cinema, or play board games. Monocarp knows that on the ith day, exactly AI friends will join him for skiing, BI friends will join him for a movie, and CI friends will join him for board games. Monocarp also knows that he can't try more than one activity in a single day. Thus, he asks you to help him choose 3 distinct days X, Y, and Z in such a way that the total number of friends to join him for the activities AX plus BY plus CZ is maximized. And for the constraints, it says that you'll have a T denoting the number of test cases, which goes up to 10 power 4. And then in each test case, you'll have N, which denotes the size of our arrays, which can go up to 10 power 5. And elements in each of our array can go up till 10 power 8. Also, there is a special condition that the sum of n overall test cases will not exceed 10 power 5 for a given test case. As we are thorough with our problem statement, let's move on to a solution. Right. So what I'm going to do now is take a sample case, and by taking that sample case, I'll explain you what the problem is really asking and what do we need to do in order to solve it. Right. So first of all, we'll see what has been given. We have 4 things. First of all, we have n, and then we have a, b, and c. N is an integer, right? And this integer denotes the size of what? Our arrays. And our arrays are a, b, and c. So a, b, and c are our arrays. So what a, b, and c represent are: a represents the number of friends that will join you on the ith day if you go skiing. B represents the number of friends that are going to join you on the ith day if you do the second activity, which is watch a movie. And C represents the number of friends that will join you on the ith day if you do the third activity, which is in our case, as mentioned in our problem, play board games. So this is what our input parameters are representing. And now, as this is clear, we'll now discuss what the problem asks of us. So what Monaco wants is to maximize the number of friends he can meet if he chooses exactly 3 different days. So let's say he chooses days number X, Y, and Z, right? And the condition is that X, Y, and Z have to be distinct. They cannot be same, distinct, right? Now, once he chooses these days X, Y, and Z, what he wants is A of X plus B of Y plus C of Z is maximized. And what does A of X represent? Basically, A of I is ith element of array A, right? Similarly, B of I represents ith element of array B, and C of I represents ith element of array C. So once he chooses 3 different indices X, Y, and Z, he wants the sum A of X plus B of Y plus C of Z to be maximized. Now this is the problem statement. Now let's try to understand it a bit better by taking a sample case. So we'll move back to our problem, and what we are going to do is take the second test case here, and we'll just copy it and paste it here. I'll be removing anything that we don't need, and I'll try to increase the font size so it is visible much better. Right. So now in this test case, we can see that this is our n and these are our arrays A, B, and C. And as you can see, all the arrays A, B, and C will have the same size, that is of n. Now, if we try to calculate the answer for this test case, what happens is monocarp can choose X, Y, and Z. So in this question, everywhere I'll be taking zero-based indexing. So I can take X equals to 0, then I can take Y equals 3 and Z equals 1. Let's see what happens. So first of all, you can see it follows a condition that X, Y, and Z have to be distinct. You can see all of them are distinct. Now what we will do is we'll calculate the sum A of X plus B of Y plus C of Z, and this comes out to be A of X, A of 0, which is this one, this is 30, plus B of 3, B of 3 is this value, that is 20, and C of 1, that is 25. And you can see that this sum comes out to be 30 plus 20, 50 plus 25, 75. So you can check for yourself also. No other triplet which follows a condition that it has to be distinct gives us a sum more than 75, and that can be seen from the fact that the answer here is also 75. So I hope that the problem statement is clear after we have discussed this sample case. Now another thing that we want to discuss here is the expected time complexity. Now we know that it has been mentioned that n overall test cases will be less than equal to 10 power 5. This is given. Now based on this fact, I want to calculate till what time complexity on the function of m, so O of f of n, where f is a function of n, till what it can go, right? So I'll scroll down a bit and we'll see that we know usually in Codeforces that in 1 second we can run around 10 power 8 operations, right? Clearly, we can run about 10 power 8 operations in 1 second. And the time complexity, the time constraints given here are 2 seconds. So it remains around the same. So 2 in 10 power 8, not big of a difference. Now if I go O of n, that is 10 power 5, no issues. If I go O of n square, that goes till 10 power 10. So I know n square won't work. But if I try O of n log n, that will be 10 power 5 into log base 2 of 10 power 5, which will be something around 20. So that will be 2 in 10 power 6. And this will run perfectly fine. So I want something that runs in O of n or O of n log n, but not O of n square, right? This won't work. But these two can work. So I want something which is nearby O of n or O of n log n. Now, as the expected time complexity is clear, we know how a solution should look like, and now we'll discuss our solution. Now, before discussing the entire solution, I would like to put forward an argument and then we'll prove it and see why does it work, right? So my argument is, let's say you have the arrays A, B, and C. Now, first of all, what I do is I sort these arrays, right? But while sorting these arrays, I maintain the original indices. So what I basically do is I rewrite these arrays in the form of element comma index, right? So if I go to my previous example up here, I can see that I have my A is 30, 20, 10, 1. So what I would do, okay, this case is already sorted but in descending order. So I'll take something which is not sorted. Let's take this case, 35, 15, and 20. So what I would do is 35, 15, 20. I would rewrite it as 30, 0, basically element comma index. and then 5 comma 1, 15 comma 2, and the last element would be 20 comma 3. Now I would sort it in descending order. You can sort it even in descending order, doesn't make a lot of difference, but for simplicity I would sort it in descending order. So what I would do is, after sorting it, it would become 30 comma 0, 20 comma 3, 15 comma 2, and 5 comma 1, right? So this would be my new array once I sort it in descending order. Now what I say is, for now just forget these values, right? I am only talking about the indices. So let's say this was I1, this was I2, this was I3, this was I4. I'm only caring about these indices, right? Because if I have the original array and I have these indices, I can get the values. There is no issue, given that I have the original array, not the sorted array. Now what I do is, I get these indices. So these indices basically represent the values if they were sorted in descending order, right? So for A, I would write I1, I2, I3, I4 based on this condition, so on till In. For array B as well, I would write it in J1, J2, J3, J4, so on till Jn. And for array C as well, I would write K1, K2, K3, K4, so on till Kn. Now my argument is that I don't need to consider the whole array to find out all my triplets. If I consider only these subarrays of size 3 and I find out all the triplets, all the valid triplets, right? Valid in a sense that if I take X, Y, and Z, they should be all distinct. So if I have a valid triplet which lies in this subarrays only, it will always contain an optimal answer. So basically, I'm saying that for any given A, B, and C, if I sort those arrays and obtain these indices, which represent basically the values if they were in descending order. And now if I consider only the subarrays of size 3, the first subarray of size 3 for all these arrays, the answer triplet will always lie within these subarrays. It will never go past it. This is my argument. Okay. And if I discuss this again for the sample case that I just took before, so let's again paste this sample here, remove everything, and increase the font size again so that it is visible. Now if I want to dry run that algorithm for this code, so you basically understand what I'm trying to do. What I'm doing now here is first assigning indices. So 30 comma 0 for array A, this is for array A, 30 comma 0, 20 comma 1, 10 comma 2, and 1 comma 3. Now for array B as well, so 30 comma 0, 5 comma 1, and then 15 comma 2, and 20 comma 3. And similarly for array C, I would do 30 comma 0, 25 comma 1, 10 comma 2, and 10 comma 3. Now I sort them in decreasing order. So my new arrays, so let's say they were A dash, B dash, C dash, they would look something like this. So the array A would look exactly the same because it was already sorted in descending order. So it would look as it is. The new array B would look something like this, as we discussed earlier: 30 comma 0, 20 comma 3, 15 comma 2, and 5 comma 1, right? And the array C also would remain the same, but If you see the little bit intricacies, that it is actually a pair. So in a pair, we compare dot first, and then dot second. Here the dot second is larger, so it would actually come in front, but that does not make a lot of difference because the dot first values are same. Now these are my new arrays, let's say, after sorting them. And now my proposition stated that you need to consider only this part, the first three. And you can see for yourself as well. Now, original answer, what did we consider? We considered 30 from array A, and then 20 from array B, and 25 from array C. And you can see the indices were 0, 3, and 1, and they're all distinct. So if I took only the indices, like I mentioned earlier, so my I1, I2, I3 would be 0, 1, and 2. J1, J2, J3 would be 0, 3, and 2. And K1, K2, K3 would be 0, 1, and 3. So what I would do, I would take I1, which is 0, J2, which is 3, and K2, which is 1. And these are all distinct. And these values were 30, 20, 25, and the sum came out to be 75, which gave me the maximum answer. So we saw that it works for this case. But now, in order to verify that our argument is correct, we need to generalize it, right? And to generalize it, we can see a simple mathematical proof. So what we do is, we have many ways to prove it, but let's take a simple way, and let's take a case where the condition xyz to be distinct. So initially the condition was xyz had to be distinct. Let's say for a moment this does not have to be true, right? We are ignoring this condition for once. Now what will be my maximum answer? It would be a of I1 plus b of j1 plus c of k1. The I1, J1, K1 are from the previous notations that we discussed earlier, right? So the maximum element from A, the maximum element from B, and the maximum element from C, right? Some of them would be my answer if they didn't have to be distinct. Now what I need to do, once I have the maximum possible answer, so you can see this is the global maximum. You can never go beyond this, irrespective of any condition on X, Y, and Z, right? So this is my maximum answer. And now if I want to move from this answer to our condition that X, Y, Z have to be distinct, so I'm now imposing this condition. I want my original answer to decrease as little as possible, right? So if my original answer was, let's say, 100, I would want to have a 90. This would work, but an 85 would not work, right? Because I have a 90 satisfying this condition. So I want it to decrease as low as possible while satisfying this condition. Now you can see, even in the worst case, let's say in the worst case, x equals y equals z. This is our worst case, right? Because in this case, we would have to move two of our indices. Either move y and z, or let's say x and y, or move y and z, or move x and z. We would not move all three, right? Because it would not be optimal, because we want to decrease as low as possible. So the more indices we change, the higher the sum we lose, right? Because as x is I1, so if we change I1 to any other index, we are going to lose sum, right? We won't increase our value, we'll only decrease it. Similarly for J1, if we change J1 to some other value, we'll only decrease it, not increase it. Similarly for K1. So we want to decrease as less of the values as possible. But if all of them are equal, we would have to move two. So one would remain same and the rest of the two would decrease. So what we could do here is, let's say in this case, we would have I1, J1, K1, and I1 equals J1 equals K1. So what we could do is, we could move J1 to J2 and K1 to K3, let's say, considering the fact that J2 equals K2. In some cases, it may be possible, it may not be possible. Sometimes it also can be that J2 is not equal to K2. So our new triplet would be I1, J2 and K2. So you can consider all the facts. It is a bit of a casework, but you can prove for yourself that in any case, we would not move past the subarray of size 3. Always, my triplet that will give me the optimal answer will always lie in the subarrays of size 3, the first subarrays of size 3. Right. You can take all the cases where any of those values are colliding, but even in any of those cases, we can see that we would not move past I3, J3 or K3, right? We would not move past any of these for our I's, J's and K's. So considering this fact, we can say that our original proposition holds true for any array, and thus it decreases our search space. So initially we were searching for the whole array. In the brute force, what we would do is we would search for the whole array and take all the triplets into consideration. But now we can see that we only need the subarray of size 3 after sorting it, right? So our search space has decreased considerably. Now a small doubt that some of you might have is how would we check, right? It seems a lot of casework that when to move J, when not to move J, when to move K, when not to move K. So do I have to write a lot of these statements? Not at all. What you can do, as you know that there are only subarrays of size 3, you can run a brute force for this subarray, right? So you can run a brute force in 3 cube, 3 power 3, can run a brute force in this complexity where you have these 3 subarrays of A, B, and C. So 3 elements in this, 3 elements in this, 3 elements in this. Take 3 pointers and move continuously move these 3 pointers. Consider all possible cases, and for each case, you just need to consider that I1, J, and K are not same, right? If I, J, K are not equal, then it is our possible answer, and then simply A of I plus B of J plus C of K would be the sum for that case, and take this maximum sum over all cases, and there will be only 3 power 3 cases because each subarray is of size 3. So taking all these 3 power 3 cases, which is 27 cases, we'll get our maximum answer, and that will always be our optimal answer in any case as well. So this is a solution. I hope you're clear with this, and we can move to our code. We'll be discussing our implementation as well as our time complexities. Right. So let's see our code. So this is our main function. What we are doing here is we are taking the test case input, and then for each test case, we are taking the size as input, and we are declaring 3 arrays and taking input for all of them, and taking an input for an array is basically O of n, right? And this would be O of n for all these 3. No issues with that. And now what we can do is check our function of find max 3 as I've written here. So what this function does is basically finding the 3 indices which denote the maximum values in that array, right? So I'm doing exactly what I stated while explaining the problem. So I'm transforming the array into our vector of pair, basically, where it would represent element comma index. So that is how I'm representing it. Dot first is value and dot second is index, and then I'm sorting it in decreasing order. And remember here that sorting, the in-bit sort function takes n log n. Now I am taking the first 3 max values and storing it in an array. So I'm taking dot second values, which will basically represent our index, and then returning those 3 values. And I'm repeating this function for all my 3 arrays because I want the size 3 subarrays for all of my 3 arrays, right? And as you can see, Here, this is an O of n loop. This is O of n, and this is O of n log n. So total function complexity will come out to be O of n log n only. So this would be O of n log n. Similarly, for all these three. Now what I do, as I stated earlier, I would just run a 3 cube brute force over these arrays of size 3 to find out my possible triplets. So let's say x, y, and z. X, y, and z are basically the ijk's of my arrays. And now I'm checking that x should not be equal to y should not be equal to z, and z should not be equal to x. As I stated, they should be distinct. And even if some of them are equal, we'll just continue. We'll not consider it as a possible answer. And if all three of them are distinct, then we would say, yes, this triplet can be a possible answer. And then we'll calculate our sum, a of x plus b of y plus c of z, and take this maximum over all test cases. Using the max function takes only O of one time, but we're running it inside three nested loops. So this would be O of 3 cube, but this is a constant value itself because it does not depend on the size of our input. So our input can be as large as possible, but we'll run these loops only till 0, from 0 till 3, right? So this is basically O of 1 because it is constant. The constant factor may be high, but it is not changing as the size changes. So this is still a constant time complexity. Now we'll output our answer, and for the time complexity, we can see, remembering the fact that the sum of n overall test cases is 10 power 5. So we don't need to worry about the t here because that would not affect our time complexities in this case. Coming to the total time complexity, the total time complexity, this would come out to be O of n log n because that is the maximum we are taking for any operations. So we are sorting here, that takes the maximum one, that is O of n log n. And the space complexity also needs to be discussed. Space complexity. As you can see here, we are just taking O of n space. So this is O of n space to store those arrays. And here as well, we are taking O of 1 space. Basically, we are storing vectors of size 3. And again, that size does not change with respect to the size of our arrays. So it is still a constant space complexity. And here it is O of n because we are making a new array, or O of 2n, but that is again O of n because we are making a new array and then sorting it. The sort function itself does not take any extra space. So the whole function takes O of n extra space, and this is also O of n, and here this is O of 1, calculating the maximum answer. So total space complexity comes out to be O of n. And as n is 10 power 5, we can see it sustains both time complexity and space complexity. Another small thing to note here is to calculate the three maximum indices, or the indices which denote the three maximum values. We always don't need to sort the arrays. We can even do it in O of n, but that just increases the implementation by a bit. So in order to simplify our implementation, and also for the fact that this question sustains the time complexity of n log n, we just sorted the array for simplicity. But this is not necessary. We can do it in O of n as well. So that is all for our problem. And for the ending remarks, I would say this problem was quite interesting for the fact that we had to optimize our search space. So initially we were thinking to run a brute force over all the possible triplets, but using some clever observations and mathematical proofs, we could see that we don't need to run our brute force over all the triplets. We can just run it over the indices representing the three max values. So only the size 3 subarrays were enough, and running a brute force over those subarrays would always give us our answer. Thank you.